Great. So my name is Jacqueline Edge, and I'm going to present work that I have done in collaboration with my colleague Laura Lander and supervised by Professor Greg Offer. And it's about the Techno-economics and sustainability assessment of electric vehicle lithium-ion batteries. So we wanted to take a step back and consider the impacts and the costs across the entire battery life cycle, considering it as a product, taking from the point of view of the extraction of the materials, going through all the manufacturing processes, through the use of the battery, and then looking at what happens at the end of life of the battery, whether you either dispose it or recycle it. The aim of our research was to identify the best possible battery in terms of that matches the requirements for a particular application in terms of sustainability, costs, and performance. And we wanted not only to consider the materials, but also the form factors, the design of the pack, and the operation of the pack. Our approach was to assess the environmental and economic impacts of the batteries across their entire value chain, so that we can identify where the hotspots are and then maximize from a whole systems perspective the environmental and economic benefits. There are many things you can do looking across the entire life cycle to reduce the overall footprint and the costs. Obviously, the most obvious thing that we do is use different, more suitable materials, and there's a lot of research in that area. But you can also look at battery manufacturing processes and recycling processes and work out how to lower their impacts, for example, by using low carbon electricity. Extending the lifetime is quite an important strategy because that extends the use of all the embodied resources and energy. And then you can improve the cycling efficiency of the batteries, so that makes them more efficient for longer. And so in the first piece of work I'm going to talk about, we focus on this use phase and the extension of lifetime. There are ways that you can extend the lifetime using different engineering solutions, and the first one we decided to look at is thermal management systems. So there are many degradation mechanisms, which you'll hear about today, which are exacerbated by either temperatures that are too high or too low. And so thermal management systems aim to keep the batteries operating at these optimal windows of temperature. But of course, when you introduce a thermal management system to the battery pack, you're also adding more materials, more resources, and more costs. So we wanted to look at what is the balance between the best thermal management system to use, which then also extends the lifetime, reducing the environmental impact. So we considered mostly life cycle costs and life cycle carbon footprint, and we looked at 4 different thermal management strategies. The easiest and cheapest is air cooling, where you simply flow air through the battery and it cools the cell that way. There's various forms of liquid cooling. You can either immerse the cells directly in a liquid cooling material, or you can indirectly flow liquids through pipes where they cool the cell either by surface contact or through the tabs. And so we assessed all 4 of these and how they impact lifetime and cost. So we used a model that was parameterized for NMC 111 graphite, that's nickel, manganese, cobalt. And so it was an EV battery pack that was used this particular chemistry. And then we assessed the 4 different types of cooling mechanisms, and you can see the results here that the impact that these cooling mechanisms have on lifetime. And you can see that air cooling is actually the worst. It has the least impact on lifetime. But if you want to extend the lifetime of your battery, then surface cooling and immersion cooling are very close to the same in improving that, and tab cooling falls somewhere in between. But this is only considering tab cooling from a very basic level. And so then we used the models to assess what the whole life cycle cost was and the carbon footprint, and this followed very much the lifetime trend. So air cooling is the worst, but surface and immersion cooling is the best in terms of lowering the cost and lowering the carbon footprint, with tab cooling somewhere in between. But then because our group has perfected tab cooling and optimized it for the specific cell design and found ways that you can reduce thermal gradients across the layers of the cell, we thought, well, what if we now try to use these optimized tab cooling mechanisms? And then when we put that model in, we found that reduced extended the lifetime even further, and that greatly reduced the life cycle costs and the carbon footprint over the whole battery life cycle. And now it actually performs much better than the surface cooling and immersion cooling. The second piece of work I want to talk about, where we focus on the recycling stages, we wanted to see what happens when you take a pack apart and what are the impacts this has and the implications for recycling. So as many of you know, the use of batteries in electric vehicle is likely to lead to significant waste of batteries. And so we want to try to not only reduce the waste by recycling batteries, we also want to displace virgin materials which have very high impacts associated with their extraction and processing. So we focused in on the recycling stages. So this is when an EV battery reaches its end of life at its 80% state of health criterion. It is then transported to a recycling facility where it is taken apart. And then it can be put through one of 3 different recycling methods. The hydro and pyrometallurgical methods are quite similar. In both of these, you shred the battery. In pyrometallurgical, you basically throw them into a very hot furnace, which is very high energy intensity. And then you reduce it down to its constituent metals through various processes. Hydrometallurgy manages to lower the costs of this by using certain chemical process instead of using high heat. And in direct recycling, the aim is to try to recover the materials and components in the batteries in pretty much their functional form so that you can put them back into remanufacture at a much more advanced stage and thereby bypass the earlier high impact phases. And then, of course, you need to balance this against all the costs of these processes against the revenue that you can get from the materials you recover. And so we looked at all of that and we found certain trends in recycling. So it's heavily influenced by the transportation costs between countries. It's also influenced by labor costs of taking the packs apart. And it's influenced by the cobalt content, which is, of course, the highest value material at the moment. So we found that for recycling to be profitable, it needs to happen in China, where the labor costs are low. You have to use direct recycling as much as possible to try and recover the highest value materials, because the electrodes, if you can recover them in their functional form, then they have a much higher value, even than the constituent metals. And of course, the high cobalt content, so the chemistries like nickel, cobalt, aluminium, have the highest revenue streams, so they're very profitable. We also looked at 2 different formulations of nickel, manganese, cobalt, so NMC 622 and 811. And we looked at low value materials such as lithium-ion phosphate and lithium manganese oxide. We found that at the moment, if you use pyrometallurgy or even hydrometallurgy, then you will have losses in the low value materials. So even though these methods are simpler and more widely used by recycling companies, they're actually the ones that give the least profit. So trending towards direct recycling is a good idea. And with the low value materials, the only way you have the option to achieve a profit is through using direct recycling methods. We also compared different countries. So if we send the packs to China, we have them disassembled there and then recycled there. The biggest problem is the transportation back to the UK so they can be put into manufacturing. But if we keep the packs in the UK and we disassemble them there, then the big problem is that the labor costs are very high. So we felt that in-country recycling is good to avoid the transportation costs, and perhaps you could avoid the labor costs by making packs much easier to take apart and by automating the pack disassembly process as much as possible. So in conclusion, we've developed these advanced techno-economic models which assess the impacts and costs, focusing at the moment just on the use phase and the recycling stage. We've demonstrated the importance of battery lifetime as a strategy for improving the whole life cycle cost and carbon footprint. And this can be achieved through engineering solutions and optimizing the design of the cell and thermal management. And we also find very narrow conditions under which battery cycling is profitable at with today's processes. There's a very strong dependence on transportation costs, labor costs, and materials revenue, which suggests that we need to adjust the logistics of the recycling supply chain, and certainly focus on how we make battery packs easier to disassemble. So that is the end of my talk. Thank you very much for your attention.